This is the fourth lesson of the second term. So we continue with gases and gas laws. So briefly, we're going to discuss the ideal gas equation. Using Avogadro's hypothesis, which states that every volume of gases at the same temperature and pressure contain the same number of particles, and also combining the three laws, which are Boyle's law, which states that the product of pressure and volume is constant. Second gas law is Charles' law, which states that the quotient of volume over temperature is constant, and Gay-Lussac's law, which states that the quotient of pressure, the temperature is constant. So combining these laws, we get PV over T is equal to NR. Making PV the subject of the formula, we get PV equal to nRT. To calculate the number of moles, we use this formula, which states that the number of moles is equal to M over molar mass, where M stands for the mass. So these quantities are as follows. P stands for pressure, which is measured in pascals. V stands for volume, which is measured in meter cubed. N stands for the number of moles, which is measured in moles. R stands for the universal gas constant, which is 8,31, which is measured in joules per Kelvin per mole. T stands for temperature, measured in Kelvin. Small letter m stands for mass, which is measured in grams. Capital letter M stands for molar mass, which is measured in grams per mole. Okay, let us take an example. So we need to convert now the units into meter cubed. Okay, the first question is, let's convert a volume of 22,4 per cubic decimeter. So we convert it as follows. So this is example number 1. Example number 1. One point one we have volume, which is given as 22,4 cubic decimeters. Okay, let's check how many meters per decimeter. So it's 10 decimeter. So which means 1 decimeter is equal to 10 to the power 1 meters. We divide by 10 both sides. So where there is a decimeter here, we're going to put a meter. So we're going to have V, which is equal to 22,4 into 10 to the power negative 1 meter. We raise it to the power 3. Okay, let's punch the calculator quickly. How much are we getting? The answer is 0,0224 meter cubed. Okay, the next question, 1.1.2. We need to convert a volume of 50 cubic centimeters. What we know is 1 meter is equal to 100 centimeters, which is the same as 10 to the power 2 centimeters. Okay, 1 meter is equal to 100 centimeters. So which means 1 centimeter is equal to 10 to the power negative 2 meters. Now let's substitute where there is centimeter cubed by a meter. So we have 10 to the power negative 2 meter all to the power 3. Okay, let's punch that into a calculator. How much are we getting? So the answer is 5,0 times 10 to the power negative 5 meter cubed. Okay, that is the answer. Let's go now to the third question. So we have volume, which is equal to 750 millimeter cubed. Okay, what we know is 1 meter is equivalent to 1,000 millimeters, which is also the same as 10 to the power 3. 1,000 can be represented by 10 to the power 3. Okay, so where there is a millimeter cubed, now we need to write a meter. So let's write 1 millimeter in terms of a meter. So it is the same as 10 to the power negative 3 meters. How do we get it? We divide by 10 to the power 3, both sides. Then we get 10 to the power negative 3 meters. Let's substitute this into a millimeter. So where there is a millimeter, we write 10 to the power negative 3 meters, because 1 millimeter is equivalent to 10 to the power negative 3 meters, or 1 millimeter is equivalent to 1/1000 meters. Then we raise it to the power 3. Okay, let us punch it into our calculator. It is the answer. So the answer is 7,5 times 10 to the power negative 7 meter cubed. Okay, so we have converted now a millimeter cubed into a meter cubed. Okay, let's go to the next question. Okay, 1.2, calculate the number of moles for the following. The first question, we have 5 grams of oxygen, yes. The second one, we have 0,001 kilograms of helium gas. Okay, let's do that together. So what are we given? So we're given a mass of 5 grams. That is 1.2.1. So this is oxygen. So oxygen is denoted by O2. That is oxygen gas, which is diatomic. So from the periodic table, the molar mass of oxygen is 16. But how many oxygen atoms do we have? We have 2 of them. So if we multiply 16 by 2, we get 32. The molar mass is given in grams per mole. Okay, let's use now the formula to calculate the number of moles. It is number of moles equal to small letter m for mass over molar mass. Then you can substitute the values. Mass is 5 grams, molar mass is 32 grams per mole. Let's divide 5 by 32. How much are we getting? 0.156 moles. Gram cancels grams. Let's go to the next question, 1.22. We're looking for the mass now of helium. So what is the molar mass of helium? It is 4 grams per mole. So the mass here is given as 0.001 kilograms. We need to convert it into grams. We multiply it by 1,000, then we get 1 grams. Okay, let us use the formula N equal to mass over molar mass, which is the same as 4. Okay, so it is the same as 1 grams over 4 gram per mole, which is the same as 0.25 moles. Yeah, so we have managed to calculate the number of moles. Let's go to the next question. Okay, so 1.3. A 1.4 mole of butane gas is enclosed in an 8 cubic decimeter domestic gas cylinder at 18 degrees Celsius. The question is to calculate the pressure of the gas in the cylinder. Okay, let's write the solutions together. One point three. Okay, let's check what are we given. The number of moles is 1.4 mole. The volume is given as 8 cubic decimeters. Let's convert it quickly. So we said 1 decimeter is the same as 10 to the power 1 meters. Then we raise it to the power 3. How much are we getting? 0.008 cubic meters. The temperature is given as 18 degrees Celsius. We need to convert it into Kelvin, so we add 273. How much are we getting? 291 Kelvin. Okay, so to calculate the pressure, we use this formula PV equal to nRT. So let's substitute. Pressure is what we are looking for. Volume is 0.008 meter cubed. And the number of moles is 1.4 moles. R is 8.31 joules per Kelvin per mole. The temperature is 291 Kelvin. So to calculate P, we make P the subject of the formula by dividing by 0.008 meter cubed to both sides. Okay, let's punch it into our calculator. So this cancels this. So in the left-hand side, we're left with P. Okay. In the right-hand side, we calculate 1.4 times 8.31 times 291, divide by 0.008. Okay. The answer is 4,23186,75 Pascal. If we divide it by 1,000, we get a kilopascal, which is 423 kilopascals. Okay, that is the answer. Let's go back to our notes. All right, difference between real and ideal gas. An ideal gas is used as a model to explain the gas laws. It obeys gas laws at all temperatures and pressures. Real gases do not obey the gas laws at high pressure and also at low temperature. Okay, let's check now gas laws at high pressure. Particles are large compared to the spaces between them. That is the real air gas. The particles of real gas are large compared to the spaces between them at high pressure. Which means as pressure increases, the volume can no longer decrease and it becomes constant. At low temperature, let's check the particles of real gas. Intermolecular forces cause the particles to stick to each other. The volume of the gas becomes constant and the pressure is lower than expected. Gases liquefy. Let's consider the table below for the differences between real and ideal gases. So ideal gases have infinitely small particles, but the real gases, they have a measurable size. Ideal gases have identical particles, but the particles of real gases, they are not identical. It is a gas mixture of various particles. Ideal gases have no intermolecular force between particles. But in real gases, we do have intermolecular forces between the particles. Ideal gases do not liquefy, but real gases, they do liquefy, for example, at low temperatures. Let's consider similarities between real and ideal gases. Ideal gases, they collide with a perfectly elastic collision. Also real gases, it is also the case. They collide with a perfectly elastic collision, which means there is no energy lost during collision. Let's consider the deviation now of real gases from the ideal gas. Okay, so the first graph, along the y-axis we have pressure, and we have along x-axis the reciprocal of the volume. So we can see then as the pressure increases, the reciprocal of the volume become a vertical line, which means it becomes constant. Now we say at high pressure, large particles take up space, so the volume no longer decreases, and the reciprocal of the volume becomes constant. Let's check now the second graph. Along x-axis we have temperature, and along y-axis we have a volume. You can see the deviation there at low temperatures, when temperature gets close to 0. So we say at low temperatures, the particles take up space and the volume cannot decrease anymore. Unlike the ideal air gas, where the temperature decreases. So let's consider this other graph. At y-axis we have pressure, At x-axis we have a temperature. So you can see that there is a deviation there at low temperature. So the deviation is denoted here by this yellow graph. At low temperature, particles are held together by intermolecular forces, and P is lower than expected. Okay, let's consider this example, example number 2. The relationship between pressure and volume was determined for two different gases, which are gases A and gas B, at constant temperature. The product of the pressure and volume values were calculated and used to plot the graph. Here you can see them. Along the x-axis we have pressure measured in pascals. Then we have along y-axis the product of pressure and V, which is measured in joules. So you can see we have a magnitude there on top of 989 joules. Okay, we have gas A and gas B. Gas A and gas B. So first question, state in words the relationship between P and V for gas A between 0 and pressure P1. Okay, you can see where this is the first one. Okay, this one is P1. Okay, then we can take this as P2. This is P1, this is P2. Okay, first question, state in words the relationship between P and V for gas A between 0 and pressure P1. Okay, let's do that together quickly. Okay, let me clear the screen. This is example 2. Okay, so 2.1. So of course, pressure here is inversely proportional to the volume. Okay, but the question says we have to state it in words. So we say pressure is inversely proportional to the volume. At constant temperature. Okay, pressure is inversely proportional to the volume at constant temperature. Okay, 2.2. Let's go to the questions for 2.2. 2.2 says, which gas, sulfur dioxide or helium, is most likely to represent gas A? Okay, let's check gas A. As you can see here, gas A, as pressure increases, deviate, less than gas B, which is sulfur dioxide. Okay, so we can say gas A is helium, not sulfur dioxide. So it is helium. Why helium? Because it behaves close to the ideal gas. So it starts deviating after the increase of pressure. Okay, let's go to the next question. 2.3. If 0.4 moles of gas A was used, calculate the temperature at which the experiment was conducted. Okay, let's do that quickly together. Two point three, we're given the number of moles N, which is 0.4 moles. Okay, what else is given in the graph? We're given PV, which is 989 joules. So we know R is the constant, which is 8.31 joules per Kelvin per mole. Okay, then we have PV equal to nRT. Let's substitute. PV is 989. She's measured, of course, in joules. The number of moles is 0.4 moles. R is 8.31 joules per Kelvin per mole. Then T is what we are looking for. Then we can divide both sides. To make T the subject of the formula, we divide by 0.4 mole times 8.31 joules per Kelvin per mole. Okay, what you do in the left hand side, we also do it in the right hand side. We divide by 0.4 mole times 8.31 joules per Kelvin per mole. Okay, let's punch the calculator quickly. What is the answer? So we get 297.53, which is in Kelvin. Okay, so to convert it into degrees Celsius, we subtract 273. Okay, the answer is 24.53, which is 25 degrees Celsius. Okay, that is the temperature. Okay, let's go back to our notes. Okay, that was 2.3. 2.4, explain why gas B deviates from ideal gas behavior at pressure P1. Yeah, let's go back to the diagram. Explain why gas B deviates from ideal gas behavior at pressure P1. Okay, pressure P1 is the first P here. So you can see there we have gas B, which deviates from the ideal gas. Okay, let's write the solutions together. Two point four. Okay. As pressure increases, intermolecular force forces pull particles closer. By so doing, they reduce. By so doing, they reduce. Reducing P and V. below those values of ideal gas. Okay, let's go back to our notes. (2.5). Explain why gas B deviates from ideal gas behavior at pressure P2. Yeah, the second P here is pressure P2. So we have gas B there. 2.5, let's answer it together quickly. (2.5). At high pressure, large particles they do what? They prevent the volume to decrease further. Yeah, as it would for ideal gas. So for ideal gas at high pressure, it was going to decrease to 0. The volume was going to decrease to 0. Okay, let's go back to our notes. 2.6. Give a reason why the PV intercept is different for the two gases. Give a reason why the PV intercept is different for the two gases. So you can say the intercept is different. So what is the reason? Let's write that together. Okay, it's because the particles they have, or the gases, they have different number of moles or different amount. So we can say the two samples of gases have different masses. Okay, that is the reason. Let's go back to our notes. Okay, learner's activity number 1. So this you need to do it by yourself at home. 1.2, 1.1, we need to convert the following units into meter cubed. The first question is 200 cubic centimeters. The second one is 200 cubic decimeters. The third one is 200 cubic millimeters. You need to convert them into meter cubed. 1.2. You need to calculate the number of moles for the mass of 8 grams of nitrogen gas. Okay, let's go now to activity number 2. 2.1. A quantity of oxygen is collected in a 280 cubic centimeters flask. The pressure of this gas at 25 degrees Celsius is 115 kilopascals. The first question is to calculate the number of moles of the gas in the flask. Second question is to calculate the mass of oxygen gas in the flask. Third question is to define ideal gases. Fourth question is to describe the principle or the properties of an ideal gas. 2.5 is to explain and describe the conditions where the real gases behave as ideal gases. 2.7, you have to explain and describe the conditions when the real gases behave as non-ideal gases. Okay, the third activity, consider the graphs below and answer the questions that will follow. The 4 graphs represent the following gases: ideal gas, nitrogen gas, helium gas, and hydrogen gas at constant temperature. So The gases there of those graphs are represented as A, B, C, and D. Along x-axis we have pressure, and along the y-axis we have the product of pressure and volume. First question, 3.1. Identify the gas represented by A, number 2 by B, number 3 by C, number 4 by D. 3.2, you need to explain your answer given in question 3.1. Learners activity number 4. The diagram below shows 3 graphs which were obtained during an investigation of Boyle's law for samples of oxygen, helium, and neon gas at the same temperature. During the investigation, equal masses for each of the gases were used. Okay, we are given the graph there. Along x-axis, we have the reciprocal of pressure per Pascal. Okay, along the dotted line, we have the amount of the reciprocal of pressure, which is 5 times 10 to the power negative 6. And along the dotted line on the y-axis, which is the volume measured in cubic decimeter, then we have 7,2. Let's consider the questions. 4.1, the first question. What does the gradient of each of the graphs represent? Number 2, which of the graphs A, B, and C are associated with gases oxygen, helium, and neon, respectively? Give a reason for your choice. 4.3, if there are 0.6 moles of gas B present in the container, calculate the temperature during the investigation. Okay, that is the end of the lessons. Thank you for taking part of the lesson. Please learn, grow, and succeed. Thank you.